Hello. Today is an exciting day because we're at the finish line. So we're building a transformer. Last time we implemented multi-headed attention, which is the last major part of the transformer. We had this question. Do you need masking in a decoder-only transformer? If no, why doesn't it learn to look ahead to predict all the non-last tokens? The answer is yes, and for the exact reason that we said. We have to prevent it from looking ahead, because remember that the input and output look like this. So you've got a list of, for me it's characters, but in general it's tokens. And that's a face of this cube. And then if you're doing multiple at the same time, then you have another axis of the cube. So this is both the input and the output. The interpretation of the input, obviously, is that this is the prompt. So each face is a prompt, and when we're doing a training, we'll have a batch, so we do multiple at once. When we're not doing training, we'll have just a single face, so it'll be a matrix as input and a matrix as output. So we are inputting a whole prompt and we're outputting a whole sentence also. So what's the interpretation of the output? Basically, for each token is kind of being treated independently, except for the attention layers. But apart from the attention layers, each token is being treated independently. So if the network is trying to predict the next token, it's trying to predict the next token for each input token. So that has some good implications and some bad implications. The good implication is that allows us to train more efficiently by, so if my prompt is, hello, my name is Clow. I want the output to be D, right? But in fact, my output is going to be a whole sentence. And we can think of it as a separate output for each input. So it might be, for H, I'm going to predict that the next letter is hello, is E. And then for E, L, etc. So each piece of text I can use as a training example where this input is supposed to have this output. So I'm basically, for each letter, I'm predicting the next letter that comes after. And then when I'm doing inference, I only care about this, the letter that's predicted after the last one from the input. So the cool thing about it is it makes the training more efficient because I have like 20 examples per example to train on. The bad thing is I'm predicting all this stuff during inference that I don't need. I only need the last letter. The other thing is, if this is my input and this is my output, I'm mostly going to be learning to cheat. I'm going to be learning to just look at what the next letter in the input was and output that here. Look at what the next letter in the input was and output that here. So, excuse me. So I'm mostly learning to cheat, and then I have a little bit I have to learn a little bit to add the next letter at the end. So to prevent cheating, we need what's called masking in the attention layer. So masking looks like this. Masked attention. You add an M here. That's going to make the attention layer not have any information from the letters that come after it. So we're adding an upper triangular matrix with zeros below the diagonal and negative infinity above the diagonal. And that's going to make it so that everything above the diagonal is what's it going to do? I think it's going to zero it away after the softmax. So after the softmax, it'll be 0. So the matrix will look something like this. What's the right way to do this? It's like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Negative infinity. I'm just gonna put a minus to mean negative infinity. So a matrix that looks like this. It should be square, so I'm missing one. But if it's square, then this should be like this. So when this is applied to the V, you multiply this row by the V column, you end up with negative infinity, or actually this will end up being that these are zeros after the softmax, I think. So your attention in that column has 0 on all of the letters that come after the first letter. And here it has 0 on all the letters that come after the second letter, etc. So it's never able to see stuff that comes after the letter that we're predicting for. So I'm going to add that to my list of goals here. This is called causal masking. And yeah, that's going to be the first thing we try to do. After that, we're going to do embedding. So I'll explain that once we get there, but let's go to attention. Causal masking. We are trying to add it right before the softmax. So here is where we would do it. M plus equals triangle matrix, causal mask, we can call it. Then maybe I want to not call this M, since M is kind of the mask matrix. Why don't I call this A, so it's like the attention. And then we want to add the mask. So NumPy upper triangular matrix. Try U. Python from NumPy, or import NumPy as np. np.tryu 44. What kind of arguments does it want? It wants a matrix as input. So let's do np.zeros 44 as a tuple. And then the second argument is, no, do I have to say k equals? No, how do I get it to, or is the try U zeroing things out? No. Okay, how does this work? Upper triangular matrix means k equals 0. Oh. Oh. Okay, so I can just say try U. And these are ones. And then if I multiply this by a scalar, which is just going to be negative infinity. Okay. Oh, that's close to what we want. We might want k equals 1. Yeah, because we want 0 in the first slot. So this is what we want. It's always the same, so it's weird to have to keep redefining it. Maybe it's fine. So it's not 4, obviously. It's going to be a.shape. Actually, I can just do a.shape here. And then I don't think it factors into the backwards pass because it's a constant. It's an addition of a constant. The constant, it's either 0 or infinity. It doesn't depend on anything else, so I don't think it gets into the derivative. So what happens if I just run this? I actually am not sure what to expect because now it can cheat less, which means maybe it'll do worse than before. But it should actually learn something. So before it was barely learning anything. It would output like the same letter over and over again, even when it was getting up to like 40%. Okay, I wondered if this was going to happen. So negative infinity is not a nice thing to put into these formulas. And yeah, it seems to have broken everything. So what's up with that? How do you put negative infinity? Okay. Causal, I might have to just look it up. Causal mask infinity. Overflow. Float negative inf. Is that different from numpy.inf? Python import numpy as np, np.inf equals float negative inf. But why would numpy.inf not work? Float negative inf. Yeah, it's the same problem. Softmax negative infinity. Causal mask. So I think I'm doing the right thing. It's just that causes overflows with our implementation of softmax. They're using the built-in PyTorch softmax. Yeah, this is what we're doing. Okay, I'm confused. I want the infinities, but log sum exp. I think log sum exp is the trick that we're using in our softmax implementation, where we're subtracting the max value. Invalid value encountered in subtract. Why is it invalid? I guess because the max is going to be not one of the negative infinities. So M is not going to have an infinity. Z is the one that will have some negative infinities. But what's up with that? You can't Python import numpy as np, np.inf plus 5. So what's the problem with the subtraction then? Like, you're not telling me that M has infinities. Print M. It does have not a number. How's it ending up with not a number? On everything, what? Okay, it starts off... Well, no, actually, it should never have negative infinity, right? Shouldn't it always pick one of the non-negative values? Oh, wait. I wonder if my upper triangular matrix is not in the right what am I trying to say? It's like, it's not the right axes. Like, it should be transposed because of the non-standard way that I have the column vectors, the first vector being the feature vector. Oh, but if I do a.shape, A is not a matrix, it's a tensor. I want the first 2 dimensions of A. How do I say that? I can do it like that. But yeah, it does need to be transposed. just trying to picture this matrix transposed. Yeah, it does need to be transposed. So actually what I want is not the upper triangular. I want the lower triangular, right? NumPy or Python from or import NumPy as np np.try np.ones 44 as a tuple. How do you do it again? You say a number first. So negative np.inf. Maximum allowed size exceeded. What? I'm confused. NumPy try. Okay, the signature is different. So here you say 44. -1. This is what I want, and then I want it multiplied by this. Oh, not a number. Oh, negative inf times 0 is giving not a number. So that was another problem. So so how do I get it to replace the ones with negative infinity? And not the zeros. I guess that's what the mask thing is doing. NumPy mask. Or I could also do it with a what do you call it? Just an expression like we did with ReLU. So it would be like isn't this basically what we're doing? Like, how are we doing it with ReLU? Times this is greater than 0. Okay. It almost works, but I'm still doing infinity times 0. NumPy replace nan with 0. Nan to num. So you just do this, and then, so it's just this, and then nan to num on that. Oh, but that replaced the infinities, but I want to keep the infinities. So there's this thing called isNan. How does that work? Okay, come on. What is this? You're indexing. That's a bit weird. I don't want to do that. There's got to be a way to just replace 1 with number. So this Boolean indexing thing is really weird. So it's, you take this and then you index in, I guess you say m equals this. No. You say m equals this. Then you say m at m equals 1 equals negative infinity. Okay. So where was I? Here. So here's my mask. Then a plus equals m. And it's not 4. It's going to be well, actually, what does it do? I will have to broadcast it, right? So I'll have to do m dot expand, or how do you do that again? I do this a million places. Expand dims. I'm going to make this a function because I use it so much. I'm just going to put it here for now. Def expand to so while x has less than the 2 shape, x adds new dimensions, return x. And then we can replace all our other while loops with this. So this would just be x equals expand dims. No, not this one. The one I just defined. Expand to, you take x and you take self.weights. And that should replace that. And then biases and x. That should replace that. Same here. Gamma equals expand to gamma x. Beta equals expand to beta x. That replaces these. Gamma equals expand to, should have done this a while ago, self.gamma d. Okay, then the thing we were actually doing. So we define M. These 2 dimensions are supposed to be a dot shape of 0, a dot shape of 1. So M is we're gonna have to expand to A. No overflows. Again, I'm not sure whether to expect it to be better or worse, because it can't cheat anymore. 23%. That's interesting because that was what the first epoch used to be before we switched to tensors and transformers. So the first epoch is no better with a transformer. This is... Actually, I don't know if that's true. I don't actually know if what I just said was right. I might be confusing it with runs that we were doing with a transformer. Okay, so 5 epochs in, I'm going to kill it and see if it can predict more than just a single random letter. What should I expect though? I'm only doing 10,000 examples, but that's not nothing. That's not very promising. Actually, forget what I just said. I don't have positional embeddings yet, so we have no reason to expect it to be able to make predictions that make any sense at all. So let's kill this. I'm gonna check off causal masking because I think we did it. It's not throwing any errors anymore. It seems as though we did it. It's hard to say until we get to see results though. The thing to try to do now is positional embedding. So let's close this. What is positional embedding? So I want to pull up a transformer here. Because our input looks like this, and almost all of the network, except for the attention layers, is acting independently on each of the columns of this cube. How do I say this? It's like the output is kind of only seeing a single letter and then giving a prediction for that. So attention solves that. Attention makes it know stuff about the other letters because the matrix multiplication between the Q and the K matrices scrambles up the letters together. And then we multiply that by the V matrix, and now we have attention scores. But although it scrambles the letters together, it doesn't know which letter is in which position in the input. It becomes just a bag of letters. The matrix multiplication doesn't remember which position the letters were in before the matrix multiplication. So because of that, we are going to add something called positional encoding. So right now our network looks kind of like this. It doesn't have this middle part because we don't have the left side. And it's also missing this positional encoding. So right here, this is the embedding. So here we're taking our tokens, which are in an 87 dimensional space in a one hot encoding, and we're projecting them into a 64 dimensional space with a learned encoding. So it gets to figure out what the weights and biases are for here. Then at the end, we unproject. So this linear here is an unprojection or an unembedding from the 64 dimensional space into the token space. So there's two things we can do. The first is GPT-2 used something called weight tying, which means the weights of these two layers are the same. It's just that this one's the transpose of this one. The reason to do that, and I was thinking about this like independently before I knew it was called weight tying, and then I looked it up, and it has a name, and it's in fact something that GPT-2 did. It forces the input and the output embedding to be the same, which means the network gets to learn twice what's a good vector space to put the tokens in. It learns it once from the input and once from the output. And what that does is it creates a semantic encoding of words. So you end up with this really cool property where you have like a vector for, if you embed the vector king, the word king, into a vector, that might be pointing like that. And then you embed the vector wife, that might be pointing, you know, downwards. What happens is when you sum the two vectors together, you end up with a vector that's close to queen. So the network, the embeddings learn to embed in a semantic way because that's what helps it do a good job on the predictions. So it helps on the output if the prompt is like, if the output is a sentence where king and queen would both be like good guesses for the next word, for the word that comes next. It's like there are probably a lot of sentences where king and queen are both good guesses. So in many ways, king and queen should be close to each other in the embedding space, because then in sentences where you could say either, the softmax should have some probability on one and some probability on the other. And that's what would make it be good at predicting text. Similarly, in the input, there are a lot of sentences where the meaning of king and queen could have been interchanged, and we should get similar predictions. Like the king knighted this person, or the queen knighted this person. The gender of the royalty is not super important to predicting the next token there. So you would want king and queen to be close to each other in the embedding, so that they would give similar predictions after going through the network. But so yeah, you get to learn the shape of the vector embedding space twice, both in the inputs and the outputs, by doing weight tying. I've also read that later networks don't use weight tying anymore, and I'm not sure why. It seems like it should be a good idea, so I don't know why GPT-3 and above stopped doing it. But yeah, that it is weight tying. So so let's do, so embedding is actually done. Like we are embedding and we are unembedding. We're not using weight tying, so they have different, we have a different vector space for the inputs and the outputs, which is fine. Positional encoding. Okay, so here's the idea is instead of encoding the letter C as a one hot that looks like 0, 0, 1, 0, 0, etc., we could encode it as C in the first position. So it's kind of like there's a different letter, there's a different encoding of the token for each position that it could be in. So it would be like 0, 0, 1, 0, 0, blah, 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 and then 1, 0, 0. So instead of being 87 dimensional, it would be 87 plus cars dimensional inputs. So this is like one way that you could do it. And then the embedding and the unembedding would be totally different, because the way the unembedding knows which character is which position in the matrix it is, but the way the embedding knows would be because it's part of the input. So you can't do weight tying if you do that, but you can do weight tying if you first embed and then do the positional encoding. Then at this point here, there's a time when it has been embedded, but it hasn't been positionally encoded yet. So yeah, that's what we're going to do. And there's a bunch of crazy ways that people have done positional encodings. Like the attention is all you need paper does this crazy thing where it adds a bunch of sines and cosines with different frequencies and a magic number of 10,000 somewhere, which seems to work well. They say in the paper that they tried doing learned embeddings also, but there was no advantage to doing it, so you might as well not do it. I'm going to do learned embeddings because the sine and cosine thing is just too hard for me to wrap my little head around. So yeah, the way the learned embeddings is going to work is instead of doing this thing where the input is C first position, we're going to do this thing. So a regular embedding followed by positional embedding, which is going to say like which is a thing that maps like 1, 2, 3, 4, 5, etc. to vectors. like whatever those vectors are. High dimensional stuff, same as the dimension, the inner dimension of our network. And then you just add the two together, embedding plus positional. So this is just an addition. Then when you're doing the back propagation, there's weights here to learn because this is it's basically a matrix multiplication. It's a linear layer where the input is constant. The input is 1, 2, 3, 4, 5, 1 for the first token, 2 for the second token, etc. So the W's can be learned, so the gradient flows back to these W's, and the gradient also flows back to the embedding. So let's try. Let's see if we can implement this. So layers. So this is going to look like the skip layer in some ways. But not in other ways. It's also going to look like a linear layer. Or maybe it'll use a linear layer. Let's just start writing, because I'm not sure exactly what it'll look like. Positional encoding. So what do? You return x plus linear of that constant matrix C. Yeah. And then the gradient back just goes equally to both of them, I think. So it's just like this. I'm getting confused here because I have a linear layer. Okay, I think this needs to be a block. And I have a linear layer. Self.linear equals linear, which means you would need to take a size. Here you do dot forward. I don't have a y, I just have a forward, an x, I mean. So the linear has its own gradients. how am I doing that in attention? In attention, I only return one delta. But shouldn't I be returning the gradients of the linear layers as well in order for them to learn? Because the outer part of the network won't optimize them. So network, if they don't get into the backprop, then they don't get updated. Okay, so I think I'm doing something wrong in attention. This needs to return the weights of the inner things. And then if I look at skip, so skip is collecting the gradients of its inner layers and then returning them all in backwards. So here, I need to replicate some of this code. So this is what you do if you want to go over them all in sequence, which is not what I want to do in the subclasses of this, but I do need this like hash stuff so I can build a big dictionary. But I guess I might need to do that separately for each of these. I just need to make sure that I replace their keys with the hash of the layer before the key. Okay, so let's do that. Matmul, I don't have to do that because there's no learnable parameters. Attention, I do have to do that. So this should work a lot better because the inner layers were not learning before. So every time I do backward, I have to make sure to keep all of those gradients. Not for matmul, those don't matter. Not for softmax, there's nothing learnable there. Not for matmul. But yes for each of these. Okay. So let's rewrite this. Grads 1, 2, and 3. All grads is a dictionary for G in grads 1, grads 2, grads 3 for key val in G dot items, all grads dot or at hash of layer. So I don't know the right way to do this. I basically want self.l1 grads 1, self.l2 grads 2. There's going to be a better way to do this that I'm going to figure out after I write it the stupid way. For layer G all grads looks like this, f of hash of layer slash key. Equals val. Did I do except delta when I was implementing lock? No, maybe I'm depending on the optimizer. Yeah, I'm skipping the ones that have delta in the name. So, okay. All grads of delta, delta 1, delta 2, delta 3, and then return all the grads. Wait, I never said what these are. These are grads 1 of delta. Now, is there a less stupid way to do this? Probably, but I think this is fine for now. Does it still work? I should be learning more now because I'm actually going to be learning the attention layers. That's not better. Which is weird. I would have thought I should be doing better, even though I don't have positional encoding yet. This is going to be so hard to debug if I add positional encoding and it's still not good. Okay. Positional encoding. No. Yes, because I already fixed the other. Or is the multi-headed... Did I not fix multi-headed backwards? Yeah, I didn't, because these linears are not learning. Or, yeah, the weights and the biases from the linear layer is not learning. So let's copy this. Oops. Copy this and make sure it applies to multi. I don't need this outer loop. Okay. I don't have a... Oh, this is not the right D here. Here I want grads of delta. And then this should say all grads at delta equals sum of deltas. And this should return all grads. So now I should be learning Okay. Now it's having trouble finding stuff that's in here through two layers. Which makes sense. I have to think about how this is set up. So skip is just a block. Here we're trying to do get attribute, and it has 2 slashes, I assume. Yes, I see 2 slashes. So I only want to split the first thing. Python 1 2 3 1 2 3 weights dot split Python split once. Yes. So let's add a comma 1 to that. Okay. Now the fact that the attention is in the multi means I think it's still not going to be learning the attention layers because I never exposed them up through the multi. I only exposed the linear in the multi. So multi, you're supposed to expose not just your linear layer, but also your heads. So when are you running your heads? Layer dot forward for layer in self dot layers except the last 2. And then when you go backwards, concat is dropping all of the information, which is not good. So concat dot backwards. I'm returning a list. Instead of a dictionary. So or it can't be concat's fault, right? Let me look at this. So we've got multi attention. Multi, when you go forward, you go through each of the layers. When you go backwards, I am going through each of the layers, but I'm grabbing only delta. Okay, so don't grab only delta. I need each of the layers to go into all grads. What am I doing here? Deltas? Let me rewrite this. So all grads is going to be, all grads delta is going to be the sum of the deltas yes, it's going to be the sum of these. Okay. I'm getting so confused because I'm using delta for so many different things. All grads of delta plus equals, here, grads equals this. And then for key value in grads.items, all grads of f of hash of layer slash key equals value. Except I don't want to be okay, fine. And then we'll just say equals sum equals delta sum. Okay. So these go backwards through the layers, each one through its respective one. And then we return the grads of all the inner things as well. This should just say equals now, and we should not do it in the loop. So are we finally learning in the attention layers now? Possibly. That's a bigger bump than before. I think I want to print what am I learning? So where does this get called? I know that's not true. Oh no, it's somewhere around here. Here. Print layer list of grads.keys. Yeah. What parameters are learning right now? So let me do this thing out here, actually. If delta in name skip, and let's take that out of each of these. Something else I wanted to do was to have something just called vanilla stochastic gradient descent. It does not need to be initialized, and the only thing it does when you call update oh, also I forgot to add a definition for optimizer. So the only thing it does when you call update is for each thing, it updates it immediately. So it doesn't need to have velocities. It just does this. It also doesn't have mu. So no velocities, which means you don't need a key. So yeah, this is vanilla stochastic gradient descent. Does that fix this? Yeah. If delta in name is not a thing, yeah, because the other thing I want to do is pass in name, I think. So pass in grad and name. So this just looks like that. You've got grad and name, so you just look like that. Grad and name, you look like this. And then for name in grads.keys, so you take name and grad. So you're for name grad in grads.items. Okay. Okay. Linears, layer norms, skip. How about after the first round of updates, just exit? So I can actually read this. So are these in any particular order? Linear, weights and biases, skip, oh yeah, these are all gonna have skip as the outermost layer. Weights, biases, weights, biases, weights, biases, weights, biases, weights, biases, weights, biases. Are these in any kind of order? Because I didn't see layer norm. Because then I've got, it looks like for this one, gamma beta, weights biases, weights biases. Oh, and then another gamma beta. These are all the same skip. 0E0. And then we get to the second skip here. 550. Weights bias, gamma beta. So that's probably, so they're not in order. Weights bias, gamma beta. Then we've got gamma beta, weights bias. So did we have the right number of weights and biases for this skip? 1, 2. Oh, we could also look at their inner thing. So the 613 would be one of the attentions. There's 2 attention heads. Is that these outer things? I don't know. Like, it's a lot. It's a lot of weights and biases, so it's probably working. I kind of have to take this and try to analyze it. 1, 2, 3. So this is probably one attention head, and this is probably the other attention head. 1, 2, 3. Then we should have, so that's the 6 that are in here. Then in the multi, we've got a linear here. So that would be these. Okay. And then 2 weights biases and 2 layer norms in the next skip. Is that right? 1 layer norm, 2 weights biases. Where's the second layer norm coming from here? Oh, these are different skips. Okay. Okay, then I think that's all of the learnable parameters. So I think we've got it now. Let's go back here, remove the line that says exit. Where is that? Let's make sure that everything is still working with the non-tensor input. That's looking good. And this should be able to say full words, I think. Well, yeah, it's a little better than the other one. But I didn't give it very much time to train. Back to tensors. Let's embed. So, positional encoding 64. Is that what I called it? Yes. Okay, so when you initialize it, this needs to be in a list. I need a custom load. It's been a while since I've tested loading. There's probably some issues with that. So this is learned positional encoding. Yeah, so when you go forward, you just add the embedding to the positional encoding, which is C is going to look like what does it look like? It's like one hot like I guess it's an identity matrix. Right? Because this is a one hot saying which location each token is in. So if the token is the second dimension, or the sequence is the second dimension, then it looks like that. So C equals np dot ones, or dot I. Import numpy as np, np dot I 6. So it's I guess it's a little complicated because it doesn't have to be square. So C X has a shape that's like 87, comma 20, comma 50. C is going to multiply X, and that needs to have the same shape. So what shape does C need to have? No, this is not right. We're going to apply W to C. This is getting kind of confusing. So what shape does the thing that's going to be, this is added, this is a plus. So these need the same shape. So W at C needs to be this. Okay, so W So it means it's something by 20 by 50. And then this needs to be 87 by something by 50. I have made a mistake somewhere. This is 64, not 87. I think all of these are 64. We're already out of 87 because we're past the embedding. Okay. So since it doesn't matter what this is, it might as well be 64. So this is size comma size. Size is going to be 64. If I go here, yeah, 64. But I could take it as an input. No, not really, because it needs to, the output needs to be the same size as the input. I feel like I might have made a mistake that this could be anything and that it does in fact have to be 64. I'm not sure. So this is I, where the shape is 64 comma 20. And how do I get that? That's x dot shape of 0, x dot shape of 1. Oh, actually, I want this to work with different orders of tensors. So it should also work like this, and it should also work like I guess there's no such thing as positional encoding when you are not at least two-dimensional, because the position is taken from the second dimension. Okay. So C looks like this. This looks right. X so C is 64 by 20. What happens if this number is bigger than this number? Then you can't use an identity matrix. Hmm. So the issue is problem when sequence length is greater than inner greater than size. I mean, what will it even do? So this is fine, but then what if this is bigger? Then you end up with tokens that don't get encoded. We don't encode positional info for those tokens. When sequence length is greater than size. Okay, I guess that just means we'll have to make sure the token space is large. Like the inner size is going to be limited to like 500. I think GPT-2 was 512. I have the paper for GPT-2 here. I guess it went up to 1,600. So we'll just have to make sure we have more than that many tokens. Right now we have 87, but we can make a tokenizer that adds more. Okay. So you must use a large token vocabulary. I'll just bite the bullet and like make sure that I do. Because I'm not sure what the easy fix for this is. Wait, am I stupid? Is this... all I need is for each of these vectors to be different. I could take any basis. Well, you can't make a basis, though, unless you have enough orthogonal directions. But could I just say, give me an almost orthogonal basis? I'll just have a to-do. To-do, I can use any basis to form my columns. Can I just use an almost orthogonal set of vectors when sequence length is greater than size? But for now, we'll just make it work. So I think this is actually it for the forward pass, right? You make this C, you do the linear, and then we'll just have to add expand dims on, or not expand dims, the thing I invented, expand to X. Okay, and then backwards, it's not delta 1 and delta 2, there's just one delta, and it goes to both of them. So delta is D, but I also want to make sure that the linear is represented. So grads equals self.linear.backward on D. Grads of delta equals D. Turn grads. No. I have to also replace their names. So all grads equals empty dict. For key val in grads.items, all grads of hash of self.layer or linear slash key equals val. Okay, there it is. So this is a full transformer if this works. Let's see. What's the issue here? Tuple object cannot be interpreted as an integer. It doesn't like the way I'm doing np.i. I guess it needs that to be two separate parameters. Sometimes it needs a tuple of a shape, and sometimes it just wants them separately, and I don't know how to know in advance. Where is it trying to do this? How did it end up with... print x.shape, c.shape, encoding.shape, and then exit. Okay, this is all expected. And then this should be 641050. Oh, I forgot to do dot shape. Good. So this looks right. Then this D should go to both, backwards to both of these guys. So here's how it goes backwards out of down to the embedding, and to go backwards into the linear, it goes like this. Then we just need to make sure to return the linears. I don't understand. How did something end up the wrong shape? Having trouble reshaping the biases. How did the biases get big? Where did this happen? Line 403. Right here. In this very linear layer. Can I print it? Where it says of size, but not shape. Where are you? It's you, right? Yeah. Print. Self.biases.shape. D.shape. .64 and D.shape is 64, 10, 50, and I'm trying to sum along everything except the first axis. I'm not seeing the problem. Oh. This guy doesn't know. I guess this should be. I was gonna say this should be D. One sec. So I'm wondering if the axes could be different for each of these, because this one, the axis that matters is D. For this one, the axes that matter are, I don't know, it could be either of them. So if I just switch this to D, does that fix it? Yeah. Okay, stop this. So again, this is it. We might be done. I'm sure we have problems, but we've implemented everything. $25.8. I was hoping for something more dramatic, because in theory, everything is here now. 30. If it keeps going up, then that will be exciting, but I guess it's possible that it only eventually becomes better, and that it starts like the same as if you didn't have positional encoding. 35. It just doesn't seem good enough. So I'm guessing I have a bug or something. Now we're plateauing. Yeah, not good so far. Like, we're not learning as fast in terms of wall time as we did with the other network. So let's kill it and say hello. Yep, that's not good. So we let it run for like 2 minutes. If I go back to the vector version, same inner dimension, the 64. How many characters have we been doing? 10. So it's a lot faster per epoch because we're doing less work. What did we get to before I cleared? I think it was 37% after 10 epochs. So maybe I spoke too soon. Maybe the transformer is working well. Is it nerfed because of the reduced training data? Because now it's plateauing here around 30. So the other network did learn better, actually. But look at this. This is such better text. Why aren't we getting this? So disaster. We implemented the positional encoding and it's still not working properly, and I don't know why, because it's not erroring. So I don't know what is not working. So I could test, I can't test attention without using the tensor inputs. But I can test multi. And I could try to make something else that uses concat. I can't test matmul though. So I could rule out multi. It's interesting that it's learning faster, but I don't like what it's learning. I'd like to see how well it's doing on the training data as well. That's easy to check. So this will make it really slow unless I take a slice of it. Wait a minute. This is good. Wait. Am I doing the... Hold on. What network was that just now? This is the tensor network. Did I just trick myself? Because that looked like the kind of text I was hoping for, and it had a higher rate than before, validation score than before. I actually do want to do this, as much as it'll slow it down. I'm interested in seeing how well it's memorizing the input also. Let's kill this, say hello. It's working. Okay. Show me how fast you memorize the input. Forgot to do this. Type the magic keystrokes that makes the percent show up well. So far you have not memorized the input that much more than you're generalizing. The gap is growing. Yeah, we're getting better at memorizing the input after 3 epochs. Something else I've been curious about is how many samples are there, training examples are there. 'Python FF data loader tensor'. $380,000. So it's going to take forever to do an epoch. It's going to take 300. It's going to take 38 times longer to do a real training epoch. So 38 times 27. It's going to take 17 minutes per training epoch. Okay, well, it might be literally working. So we're going to end it here on a high note. Potentially having accomplished the goal. I mean, not quite. I don't have a large language model yet. I have a model that could be trained into a large language model. But I'm going to do some of the kind of experimentation that takes a long time between streams. And next time we should be hopefully ready to I don't know, actually. I don't know what the next step is. But hopefully I'll have some cool trained models to show off next time and we can see how they do. But that'll be it for now. I hope this was helpful. Thanks for watching.